Hello students, my name is Shashank Shekhar. Today we'll start the new chapter, that is classification of elements and periodicity in properties. In this chapter our main aim is to see the historic development. First of all, we will see the historic development, that how do we came to this modern periodic law, and we will see that what was the reason and what were the logical steps the people in history took to finally boil to the electronic configuration part. Okay, so I would say that today's modern periodic law is basically based on the electronic configuration. So we'll see to it how we came to it. We'll see that. So after that, first once we classify the elements, or once we arrange those elements as per the electronic configuration, then we will try to see the physical and chemical properties. So that is the whole roadmap that we will follow in studying this chapter. So first of all, I would try to focus on why we need to classify this element. What was the motive behind it? So we know that the element are the basic unit of all types of matter. So if you look around you, then you see wood, you see a door, you see wall, fan, table. Okay, so each of this matter that you see around yourself is consisted of element. So means element is the one which gets together, makes the bond, complete the molecule, and that molecule holds up together to bring the matter that you see. Okay, so that is the thing we know. So this element, basically, if I talk about the element, then the number of element is large. Okay, there are vast number of elements that are present. So in 1800 there were only 31 elements. In 1865 it become double, so it was 63, and at present it is 118. So it is very difficult to say remember the physical and chemical properties of each of this element individually. Okay, so to make things easier, what do? We just try to group those elements which have similar properties in one set, so that if you know the property of the one, you can predict the property of the rest of the elements. Okay, so that is the main motive behind your classification. So your main motive is what? To study the property. So that is the reason we focus, or your exam also focuses mainly on the trends in the physical and chemical properties, because the motive of the classification is that we want to study the properties of element, but in a more designed way, or you can say in a more progressive way, so that you don't have to remember individually each of this. Clear? Okay, so if I put a picture of the modern periodic table in front of you, it looks like this. Okay, so you must have seen here and there this modern periodic table. So various parts of this are given here. So I will once I get to the history, once I make you understand the history of this development of this periodic table, we will get back to this picture. Okay, and I will let you know that what are the say classification, or what are the elements that are present here, why are they present here, what is the motive behind putting them in such order. Okay, so we will study that. Okay, so first of all, so as I have said that yes, it is we are having a large number of elements, so it is difficult to study them individually. So to ease that problem out, scientists classified them so that we can just know the properties of one, and by knowing the property of one, we can predict the property of the rest of the element. Okay, so first was Dobereiner laws of triads. So this was the first classification, I would say, that was attempted to classify the elements. Okay, so a German scientist named Johann Dobereiner in 1800, he was the first to observe the properties, or you can say the trend in properties of the elements. Okay, he noted that a similarity among the chemical and physical properties of several groups of three elements. So his law is named as Dobereiner law of triads. So basically, he does what did he did? He did try to classify elements in the group of three. So three we make bunches of three, and each of these three elements will exhibit similar properties. Okay, Now, what was the sense behind dividing them? Means what? How did they say that okay, these three elements? Because we can't study the physical and chemical properties and just say okay, these three has the same physical properties, so we are putting it on the same group. Okay, so there must be some logic behind it. So the logic behind his classification was that if you just arrange three elements in an order, then he found that the middle one, okay, the middle one atomic mass is equals to the average of the atomic mass of the element that are present on the either side. Okay, so what he took as a basis was the atomic weight, and he said that okay, we arrange these elements in the increasing order of atomic weight, these three elements in the increasing order of atomic weight, and the one which is in the middle will have the atomic mass, and this atomic weight will be equals to the average on of the element that are present on the either side. So these are some triads. Here you can see, okay, here you can see these are the atomic weights. So if you just add 7 plus 39, it will give you 7 9 16 and 314 for 46. So 46 divided by 2, that would give you 23. Okay, similarly 40 plus 137, it will give you 177. So it is on dividing it by 2, you will get as 2 8 just 16, 2 8 just 16, so approximately 88. Similarly, if I talk about bromine, so 7 5 12 336 162.5. So if you divide it by 2 again, so that would give you 2 8 just 16. So this is the atomic weight of the middle one of all of these three are kind of falling approximately equals to the average of the element that are present on the up and down side, okay, or in the either side. Clear? So this is one triad: lithium, sodium, potassium. This is another triad: calcium, strontium, barium. And this is the third triad that we have: bromine, chlorine, bromine, and iodine. Is this clear? Okay, so this is known as the Dobereiner law of triads. Now, the properties of the middle elements in between those of the two elements, all these three elements have the same properties, means they kind of are having the same property. Now, the next one who was able to classify this element was a French geologist named A.E.V.T. Cancortis in 1862. Okay, he just simply arranged the element in the increasing order of atomic weight. Okay, so what did he do? He just arranged them in the increasing order of atomic weight and made a cylindrical table of elements to display the periodic recurrences of properties. So what is the meaning of this periodic recurrences of properties? It means that see, first what did he do? He just arranged the element in a cylindrical fashion and in the increasing order of atomic weight, and he observed that in that order there is a recurrence, means there is a repetence of the properties, means properties are repeated when we are moving from lower atomic weight to higher atomic weight. Now this does not attracted much attention because it was some kind of factual, I would say, because most of this recurring was not that much appropriate. Okay, so this is the way he tried to do so. So this is the way he hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen. So this is one cylinder. Of course, this is another cylinder, and silicon, chlorine, calcium. So this is the law that I was talking about. That is your cylindrical, okay, cylindrical table of elements. Next is Newlands Law of Octaves. Okay, so an English chemist named John Alexander Newland in 1865 he founded the law of octaves. So like we have the law of triads, here is the law of octave, means 8 elements, means a group of 8 elements. So he arranged the element in the increasing order of the atomic weight and noted that every 8th element had properties similar to the first element. So it goes in this way. So suppose I have just arranged the elements in the increasing order of atomic number. Now we started to count them. So 1, 2, 3, 4, 5, 6, 7, 8. So as we count the 8th element, then the properties of this 8th element is kind of in resemblance with the properties of the first element from where we have started the counting. Similarly, if I move to the second element, then the 9th element, okay, means with respect to the second element, the 8th element is the 9th element. Okay, so these two have the same property. So this is the relationship that he tried to build. So he just compared this relationship with the notes of music. So in Hindi we have sare gama, that is your notes. Okay. Similarly, we have it in English also. Miss, I would not say in English. So in Indian culture we have this sare gama. Similarly, in Western culture also we have a kind of octave. So he compared this as octaves. Okay, he compared this trend as to the octave law. Okay, to the octave of the music. But what was the difficulty with this law of octaves? So it was only good up to calcium. Means up to calcium this trend was good, but after calcium this failed. Okay. So although his idea was not widely acceptable at this time, but he was later awarded Davy Medal in 1887 by the Royal Society of London. So this is the thing I'm talking about. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so after eighth element, the property is repeated. So lithium and sodium will have the same property. So lithium, sodium, and calcium will have the same property. Beryllium, magnesium, and calcium will have the same property. Boron, aluminum will have the same property. So in this way, the one which is in one line are having the same properties. Okay, clear? Now let us move to the modern periodic table. Okay, so this modern periodic table, the periodic table as we know today, it owes to the development of Russian chemist Dmitry Mendeleev. Okay, so he was the one who formulated a kind of very better and a very close approach to the periodic table that is existing today. There is a very you can say, I would not say that it is a very small change in the law, but a very significant change in the law. But still, his bases were different in compared to the modern law, but still he was able to construct a table that is in a very good resemblance with the current form of table, modern periodic table. But we cannot just ignore his contribution, because with the limitation of the sources that we have at those time, he constructed a very good table. So there are some very unique properties about this table, or you can say some strange properties about this table that made this periodic table popular. Okay, so two of the scientists named Dmitry Mendeleev and Lothar Meyer. So the modern periodic, the construct of the modern periodic table, the contribution of the construct of the modern periodic table goes to these two scientists. Now they both worked independently, means there is no relation between their work. So both the chemists in 1869 proposed that an arranging elements in the order of the atomic weight, if you just arrange them in the order of the atomic weight, they are having the same physical and chemical properties at regular interval. Okay, so Lothar Meyer plotted the physical properties such as atomic weight, melting point, and boiling point against the atomic weight and obtained a periodically repeatedly pattern. Unlike Newland, Lothar Meyer observed a change in the length of the repeating pattern. So what was different from the Newland and Lothar Meyer? Means see, Newland has also done the same thing. He has just arranged them in the increasing order of, say, atomic weight, but he restricted the kind of repetance. He said that okay, we can take the group of 8. So he restricted this, but in case of Lothar Meyer, he does not put any such restriction. So whenever there is a change in properties, he changed it. Okay, he simply changed it. He does not say that it will be a group of 8 or it will be a group of 3. He does not mention anything. He just simply said that okay, we are just trying to arrange it, and whenever some properties differ, we will try to find a new position that is in a good accordance with the physical and chemical properties. Okay, so see, this is the thing. So lithium, beryllium, carbon. Okay, then again sodium, magnesium, aluminum. Then again he goes up. See, here he goes up to triad. Then he take 8 element. So in this way, he just observe the properties. So what are we plotting here? Atomic volume against atomic mass. Clear? So this is the difference between Lothar Meyer and other scientists that have contributed toward the periodic table. He does not define a set. Okay, he does not say that okay, it will be a group of 8 or it will be a group of 3. He does not say that. So Lothar Meyer developed a table of elements that closely resembles the modern periodic table. However, his work was not published until the work of Dmitry Mendeleev, who is generally credited with the development of modern periodic table. Okay, while Dobereiner initiated the study of periodic table, it was Mendeleev who was responsible for publishing the periodic law for the first time. So these are just facts. You can just go through them. Now comes the main part. So he said that, okay, Dmitry Mendeleev said that the properties of the element. So what properties? Chemical properties, physical properties. So every property that you think of are just a periodic function of the atomic weight. Okay, they are just a periodic function of the atomic weight. So this is the law that was put upon by Mendeleev, and it was the basis of his classification. So this thing should be kept in should be in your mind, that according to Mendeleev, the atomic weight are the periodic function of the the properties of the are the periodic function of the atomic weight. Okay. Now when we move forward, they will see that, okay, this line goes same, but at last we don't write atomic weight, we take a different property. So we'll see. Now, Mendeleev arranged elements in a horizontal and vertical column of a table in order of their increasing atomic weight in such a way that the element with similar properties occupy the same vertical group. What is the meaning of this? So the good thing about Mendeleev was that he does not put a restriction. Okay, he does not put a restriction. Okay, we are going to the increasing atomic weight, so we will go in this way. We will try to classify it in a solid form, or there is a kind of structured periodic table. He was not. You can say he was not rigid. Okay, he was not rigid. He said that, okay, if we are going to the atomic weight, well and good. I don't have any problem with it. But as soon as I found that it is not matching, means the vertical row is not having the same physical properties, I will find the row which is having the same physical properties. I will put that element there. Okay, so that is the main crux of the Mendeleev periodic table. Okay, so Mendeleev's system of classification was more elaborative than Lothar Meyer. He fully recognized the significance of periodicity and used broader range of physical and chemical properties to classify the elements. So he was trying to classify them, means if he saw that, okay, this has the okay, so suppose 5 elements have the same physical properties and chemical properties, he would just put those 5 elements in the same vertical row and those in the increasing order of the atomic weight. Okay, so this was the main motivation behind his classification, whereas Lothar Meyer simply plotted a graph. Okay, was just simply plotting a graph. He does not study the physical and chemical properties. He just said that, okay, this is, he took one physical property, he took the atomic weight and just plotted a graph. Okay, but what did Mendeleev do? He first observed the physical properties, arranged them, then arranged them in the increasing order of the atomic weight. Now, in particular, Mendeleev relied on the similarities in empirical formula and properties of compound formed by the element. He realized that some of the element did not fit in his scheme of classification if the order was studied, if the atomic weight was strictly followed. See, he was liberal in liberal in classification. He ignored the order of atomic weights, thinking that atomic measurement might be incorrect. So this was the thing. He said that, okay, I am just putting it in the increasing order atomic weight, but if I saw that they are not showing the resemblance in the physical and chemical properties, I will not put that element there. And what was his idea behind it? Okay, his idea was that since we are not very good at spectroscopic method, so we are kind of doing a mistake in calculating the atomic weight. So he was assuming that, and then he was totally going with the physical and chemical properties. So his first priority was physical and chemical properties. Okay. So for example, iodine with a lower atomic weight than that of tellurium was placed in group 6, although along with the fluorine, chlorine, bromine, because of similarity in properties. So this is the beauty of Mendeleev, kind of, yeah. So okay, so he was going with the atomic weight in first hand, but when he saw that, okay, we don't have the same physical and chemical properties, and what is the point of classifying them? Okay, so we are not here to just classify them according to the atomic weight. So this thing can be done by anyone. So I am here to just classify in the way that they the set of elements that are present in the same vertical row, okay, they should have the same physical and chemical properties. So his he cleared his motive that okay, we are doing classification, we will do the classification only. We will not be abide by some laws or rules. Okay, so one of the example that is given here is that okay, so if you talk about say iodine, then here it has a lower atomic weight than that of tellurium. Now, if it has a lower atomic weight, then it would come before tellurium in the period. If you just see the period, then it should have come before the tellurium. But since it is showing a resemblance in the property with that of fluorine, chlorine, and bromine, he placed iodine in the group of that elements and not in the group 6. Okay. Again, one more example is there. So both gallium and germanium were unknown to the Mendeleev published in periodic table. So this is the strange thing that I was talking about. So he not only predicted that this is the way to classify the elements, he also predicted that there are some gaps. Okay, there are some gaps, and those gaps will be filled later on when we will discover those elements. So he kind of told the future. Okay, he told the future, or he predicted the future, that this vacancies will be filled up by the new elements that will be discovered in the future with a good way, with a good technology. Okay, now the gap he left was under silicon. So we'll see this say Mendeleev periodic table. So the gap why he left was under aluminum and a gap under silicon. So the gap under he left under aluminum, he called that element as eka aluminum, and under silicon he called that element as eka silicon. So this was the beauty of Mendeleev. So he not only predicted the proper say elements, that okay, this element will be found in future. He also predicted the physical and chemical properties of those. Okay, so this is something very unique to the Mendeleev table. That okay, so this is strange. Just think of it in a way that okay, you are not knowing about an element till now. Suppose I am not knowing about iron. Okay, but I will say that there will be an element in future that will be placed here whose name will be iron. Okay, so the name can be anything. Means there will be element which will be placed here, and see, these are the list of physical and chemical properties it will have. Okay, so it is you can think of it in a way that you are predicting that okay, a boy will be born or a girl will be born. So this is the first prediction, and the second prediction we are saying that this boy will have this properties. Okay, so he will have this is good qualities, and this bad qualities, and he will become a doctor or engineer in future. So this is the way you can think of it, that how fascinating it was. Clear? Now this element were discovered later on, and some were predicted by the Mendeleev, and those found experimentally. Okay, so this is the kind of Mendeleev prediction of eka silicon and eka aluminum and eka silicon. So the gallium is known as eka aluminum, and the silicon is known germanium is known as eka silicon. So he predicted. What are the predictions? See, what are the predictions? You will be fascinated by it. He predicted atomic weight of eka aluminum as 68, which was found to be 70. Okay. He predicted density to be 5.9, that was found to be 5.94. Melting point was kind of difficulty. He predicted very low. So some of course there are some limitations, but still he got a very close approximation to other properties. Now, what is the form of oxide? He also predicted that. He told that it will form oxide of the form E2O3, and that is the truth. It forms Ga2O3. He said that the chloride that will be formed by the Mendeleev is ECl3. Okay, sorry, chloride that will be formed by the eka aluminum or the gallium will be ECl3, and yes, it came out to be GaCl3. Now, talking about germanium, he said that the atomic weight will be 72. It is 72.6. He predicted density to be 5.5. It came out to be 5.36. Okay, again, the difficulty with the melting point remained. He predicted it very high, which came out to be 1231. Now, it will form oxide of the form EO2. And it's very true, germanium forms an oxide of the form GeO2. Similarly, he said that it will form the chloride of the form ECl4, and yes, it is GeCl4. Now, let us look at the Mendeleev periodic table. So, this is the Mendeleev periodic table. See, we have helium, hydrogen, okay, beryllium, boron, carbon, nitrogen, oxygen, fluorine, argon, potassium. So he placed these elements here, right? He is placing the noble gases here, and he placed these elements here. So this is the way he tried to order. Now, if you see here, you will find that there are some gaps that are left in between. So here is one gap. Okay, here is one gap that is left. Here is one gap that is left. So these are the places he said that, okay, we will in future find some elements that will occupy these places. Okay, so this is the periodic table. Now you can see how good is it in good resemblance with the modern periodic table that we have. Clear? Okay. So this was all about today's lecture. With this, I end my lecture. Thank you.